Hi everyone. In this video, we are going to cover the answer key for problem set 8. Problem set 8 introduces us to the concept of hypothesis testing, specifically one sample hypothesis testing. Keep in mind that hypothesis testing is a way that we can conduct inferential statistical tests that use sample data to evaluate the probability of a hypothesis about a population. As I had mentioned, this problem set is only about one sample hypothesis tests. Problem set 9 will cover two sample hypothesis tests, and problem set 10 is going to be a mix of both. And so what I really want to start with these questions is first identifying how we would, in a problem set 10 or in a future quiz, identify what type of test we are conducting. And so let's take a look at question number 1. Nationwide, 34% of all reported burglaries involve forced entry. In a study of burglary cases handled by a St. Louis police department, 14 out of 64 reported burglaries involved forced entry. Is there a significant difference between this department's proportion of forced entry burglaries compared to the national proportion at an alpha level of 0.05? You must complete the 5-step model of hypothesis testing and show your work to receive full credit, and please round your Z obtained value to the hundredths place. And so, as I had mentioned in both problem set 10 and our last quiz of the semester, I will not be distinguishing between one sample and two sample as I am for both problem set 8 and 9. So you might be asking yourself, how would I actually decide this in those contexts? Well, let's take a look here. As a reminder, one sample hypothesis testing is always going to be comparing a singular group to a wider population. And so within the context of question number 1, I see right off the bat, our very first word is nationwide, which tells me I have a very large population here, right? The entire nation. And so my second group here is the St. Louis Police Department, which serves as my singular group, right? So I'm comparing the St. Louis Police Department to all reported burglaries nationwide. So my one group versus a population. That's how I know it's a one sample hypothesis test. The second component of my decision making, though, is whether or not I am conducting a test for means or for proportions. And our second word is our giveaway here. I see that I have 34%. And I know that the relationship between proportions and percentages is really easy to move back and forth, right? If I need to convert this percentage into a proportion, all I have to do is divide it by 100. And so with that being said, I know that in the context of this question, I will be conducting a one sample hypothesis test for proportions. With that being said, now I can start our 5-step model. The very first step to any of our hypothesis testing is to state our assumptions. And when we state our assumptions, it is going to depend on whether you are conducting a one sample or a two sample test, and whether that is for means or for proportions. And so, specifically for a one sample hypothesis test for proportions, we assume that we are working with a random sample, that the variable we are testing is nominal, and because our sample size exceeds 50, the sampling distribution will be normal. Our assumptions here have to actually be met, and if we are in violation of any of them, we should not proceed with conducting the rest of the test. So essentially, this is our checklist. We have to make sure that we are actually checking these off and making sure we are abiding by each of these. And so here, we see that we have a random sample. We have a nominal variable here because we are only looking at burglaries. And my sample of St. Louis Police Department cases here is 64. So we do see that we exceed our 50 threshold here. So we have a check mark for each one. So we can proceed to the next step. Next, we have to state our hypotheses. Specifically, we have to do this with statistical notation. And what do I mean by that? That's what you see listed here below. We always have to state both our null and our alternative hypothesis. As a reminder, Our null hypothesis is our statement of no difference. I wrote this out for you here. You do not have to write this, but if it's helpful for you, go ahead and do it. But all I would expect from you are these symbols here, along with our pi symbol in our 0.34. But any of the text you see written here is not required. I simply have it here so that you can see it on the answer key. So let's take a look. Our null hypothesis will always be designated by H with a subscript of 0. If it's helpful for you, because I know we're in an online class here and it can be difficult to get the subscripts, if you just do H with a 0, that's perfectly fine. No worries there at all. So that's perfectly fine with me. So we have H subscript 0 with a colon. In the next decision point here comes with whether or not we are conducting a test for proportions or for means. And if you're having a little bit of trouble with that, go ahead and look back at slide number 9 from this week's PowerPoint. This tells you about the different sample statistics and population parameter symbols that we have to use in the context of hypothesis testing. Because we know that we are conducting a test for proportions, we are always going to be using population parameters. And specifically for proportions, we use the pi symbol, and we will be using that for both our null and alternative hypothesis. You can designate your alternative hypothesis by either an H1 or an HA. Again, if you want to type that out by just doing H1 or HA like that, perfectly fine. If you do the subscript, that's great as well. And so again, because our null hypothesis is always our statement of no difference, you should always have an equal sign here. Because this is comparing to a national population and we are doing population parameters, we are always going to be equaling our population parameter, which is our nationwide percentage of 34%. But again, since this is a proportion, we are converting that into 1. So 0.34. The key for our alternative hypothesis here is going back to the context of the question to figure out what direction we are interested in for the purpose of our hypothesis test in testing. So let's take a look at our third sentence here. Is there a significant difference between this department's proportion of forced entry burglaries compared to the national proportion at an alpha level of 0.05? Our key word here is difference. Reason being is we are not specifying a direction that we are interested in for the purposes of our standard normal curve. It's not less than, it's not greater than, it's not increased or decreased. It's either direction. And because of that, we use the not equal to sign. So there is a difference between burglary cases handled in St. Louis versus nationally. So again, for step 2, all you have to write down is this statistical notation here. None of this text is necessary. Our third step here is selecting our sampling distribution and our alpha cutoff level for 0.05. I got 0.05 because it's specified here in the question. And so we always know we're going to be conducting a z-test here. And the alpha cutoff for 0.05 for a two-tailed test, which again comes from what we just decided in step 2 here, that it's no difference. For a little visual here, I'm going to sneak over to our final conclusion here. But what do I mean by two-tail? Again, both ends of our standard normal curve, both directions are in play here. So coming back up here to step number 3, for an alpha level of 0.05 for a two-tailed test, I'm simply taking this from our PowerPoint itself. If you need a reminder of where this chart comes from, you can go ahead and look on slide 30 of this week's PowerPoint. Go ahead and use it as a reference. Make sure you note that for both problem sets and future quizzes. I'm not trying to trick you on these. I'm really only going to be using these alpha levels for any other problem sets or quizzes moving forward. And so you don't need to memorize these, just have this again as your reference moving forward. It will always be one of these tail values. So again, alpha level of 0.05 plus or minus 1.96, again, accounting for both ends of the tail there. And so those are going to serve as our critical value cutoff point. So that's what we are testing against. Essentially, we set up our boundary markers on both ends of our normal distribution. Step 4 is computing our actual test statistic. So this is where we're figuring out where we actually land on our normal distribution. I'm going to scroll back up here a little bit because we're going to have to pull our information from the question itself here. So when we compute the test statistic, we need to pull the information from our problem in order to do that. So based on the problem, we know quite a bit of information. Our proportion from our sample statistic comes from our St. Louis Police Department here, that 14 out of 64 reported burglaries involved forced entry. Again, I know I can calculate a quick proportion value here to get 0.22. I also know that my population parameter here for nationwide was 34%. Again, can quickly convert that into a proportion by dividing by 100 to get 0.34. And the last little bit of information I need here is the total number of sample here. So our N equals 64. As a reminder, our base formula here for a one sample test for proportions is listed right here. You'll see that we have all of the information we need here. It's only 3 pieces. Again, our P symbol, so our proportion for our sample, our population parameter for our proportion, and our N, so our sample size. This is me simply working through each of those steps here. Again, it's going to depend where you rounded here. You can see that I went to the hundredths position, and so I received a Z obtained value of approximately negative 2.03. If you were somewhere close to there with the hundredths value, I did not dock for that. Again, I understand that that's a rounding thing within the problem itself, and so no worries there at all. Again, it's really helpful for me to see you work through your steps so that if there were any errors along the way, I can kind of see where they're at and leave individual feedback on your problem sets so that I can see if there was a calculation error. So just keep that in mind. That's really why I do have you show your work here so that I can help you out if there is a calculation error that occurs. So again, Z obtained is negative 2.03 approximately, right? Anywhere right around that. So our very last step here is to make a decision and interpret our results within the context of the problem. That is our key here. A lot of you stopped at simply this step here, just with our Z obtained here and not taking the final concluding step of actually making sure what this meant for our problem, right? If you were asked to conduct this test as an actual researcher or statistician, and you went back to the police department who was interested in knowing this information, and you just gave them this Z obtained value, but didn't actually tell them what they meant, that would be a problem, right? So we always want to make sure that we're actually providing context for what this means. I always find it really helpful to actually chart this out in a standard normal curve format. I do this all the time with these types of problems. So again, what we set up in step number 3 here were our critical value boundary points. And so that's what I have here. The shaded regions are our rejection points, and the white region here is our failed to reject point. So if our Z obtained value falls anywhere within this white area, we are going to fail to reject the null hypothesis. If it lands in either of the shaded regions, we are going to reject the null hypothesis. And so here we see that our Z obtained value is approximately negative 2.03. And so we did fall into the shaded region here. Here is an example interpretation of what this means within the context of the problem. One key note about step 5 is we always have to use one or the other key phrase here. That is either we reject the null hypothesis or we fail to reject the null hypothesis. There is no accepting the null hypothesis or rejecting and accepting the null hypothesis. It's only those 2 key terms. So keep that in mind. But again, just don't say fail to reject or reject. we want to make sure it's within the context of the problem. So let's take a look at this example here. Given that our z obtained value of negative 2.03 falls beyond our critical region of negative 1.96, again, fall beyond mean we're in our danger zone here, our rejection zone, we reject the null hypothesis and conclude that the proportion of burglaries that involved forced entry in the St. Louis Police Department is significantly different than the proportion of burglaries that involved forced entry nationwide. What's very important here as well is that the language we use in our interpretation matches what we had set up in step number 2 and what the question itself was answering, right? So let's go back to step 2. We have a not equal sign because the question itself was asking, is there a significant difference, right? So that is the language we are going to keep consistent with in our interpretation. So keep that in mind. We always just want to answer what the question was asking and not make any more conclusions or less than other than what we are actually being asked to do. And so use this type of format for any other type of hypothesis testing, right? You can always use the shell formula of given that our z obtained of blank either falls beyond or does not fall beyond our critical region of blank, we either fail to reject or reject the null hypothesis and conclude that blank, right? And you can fill that in with whatever the context is of that given problem. And so keep that in mind. Go back to our PowerPoint slides and see those 2 examples written out. I have one for both proportions and for means, and this answer key as well, right? We're going to head to question 2 now and see an example for means, but this is how you work through each of the steps of the 5-step model. And so let's head over to question number 2. According to national data, the average number of use of force incidents reported by mid-sized police departments across the United States is 15.8 incidents per month, with a population standard deviation of 6.2. A researcher wants to know whether the average number of use of force incidents significantly decreased following the implementation of a new de-escalation training program. She randomly samples 30 mid-sized departments that adopted the program and finds that the average number of incidents per month is 14.6. Is there evidence that use of force incidents significantly decreased after the implementation of the training at an alpha level of 0.1? You must complete the 5-step model of hypothesis testing and show your work to receive full credit, and please round your z obtained value to the 100th place. So again, just like we did for question number 1, we need to determine what type of test we are conducting here. So right off the bat, kind of have similar situation to what we saw in question number 1. We're tipped off that we are using national data here. So that should tell us that we are comparing one group to a very large population, in this case, national data. And so I see national data, the average number of use of force incidents reported by mid-sized police departments across the United States is 15.8 incidents per month with a population standard deviation of 6.2. So now she randomly samples 30 mid-sized police departments that adopted a new training program, and that incident per month is 14.6. And so that's what we're working with here. And so we have one group versus the entire population. All right, so that tells me that I'm working with one sample because, again, we have one group compared to the entire population. So now we have to figure out, are we working with means or with proportions? And that comes also within our very first sentence here. I see the average number of use of force incidents reported by mid-sized police departments. And so we know that the word average is very interchangeable with the word mean. And so that tells me, even within our first sentence again, that I will be conducting a one sample test for means. Okay, with that in mind, we now know what test we are going to conduct. So let's go over our very first step, which is to state our assumptions. Okay, assumption number 1 for a one sample test for means is that we are working with an independent random sample. We see that our researcher here randomly sampled 30 mid-sized police departments. Let's take a look here. The variable we are testing is interval ratio for our second assumption here. We know that number of incidents is interval ratio, right? Because we can just count what those are and they have an even scale between them that is numerical in value. But let's take a look at our third assumption here. And there is a reason that I have it highlighted in red here. Because n is greater than 50, the sampling distribution will be normal. Okay, we ran into a little bit of an issue here. This is where I wanted you to actually check if this violation occurred. In other words, was this assumption met? And in this case, we actually did violate it, right? Because we only had 30 mid-sized police departments. And so we actually should not proceed with conducting this test because our sample size is too small. And we can't guarantee that our sampling distribution would be normal as a result of this. And so if you were able to identify this, you could actually stop after step number 1 and say, no, we should not proceed with this because we are in violation of our assumptions and we should not proceed with this test. For the sake of this particular problem set, I am not docking points for this at this time, but it is something I want you to be cognizant of moving forward. Again, we can't assume this every single time, right? We actively have to check these steps. Again, think of it as a checklist that we have to guarantee that we are meeting each of these requirements in order to proceed to the following steps. So, like I said, I'm not docking for it this time. Keep this in mind for both problem set 9, 10, and our future quizzes. But for the sake of this problem set, I'm going to proceed with the following steps so you can see how it would be worked out theoretically. But again, know that because our sample size is so small here, we actually should not be proceeding with the rest of these steps. Okay, let's move on to how we would conduct step number 2. Stating our hypotheses, again, within statistical notation. Here I have my null hypothesis, which is designated by H with a subscript of 0. Here you'll see that the symbol changes though from what we saw in question number 1. We had a pi symbol before for a population parameter, but now I'm seeing a different symbol, which is called mu. And the reason that it changes is because we are now using means. And so that is a switch where it's a really tiny detail, but it does make a big difference. And it does show that we are moving from a population parameter from proportions to means. And again, look back at slide number 9 from this week's PowerPoint for the chart that shows you the different symbols that we use for both population parameters and sample statistics for both means, proportions, standard deviations, variance, and sample sizes. So because we're using means here, we have our statement of no difference for our null hypothesis. So we have that our population parameter for our mean equals 15.8. Reason being is because that is our national average of use of force incidents across the United States. So we see that here. And then we see that our mu symbol here is accompanied by a less than symbol. Let's take a look at the reason why. This is different from what we saw in question number 1 because we were only interested in whether or not it was different, right? So we had the not equal to sign here. But in this case, the researcher wanted to know if there was enough evidence that the use of force incidents significantly decreased after the implementation of the training at an alpha level of 0.1. Because of that, our symbol here changes, and this is our alternative hypothesis again. You can either designate that by H1 or HA. Either one is perfectly fine. And so that is where our symbol here changes as well. That is what we are primarily interested in testing. Essentially, did this training program work, right? Did it decrease use of force incidents after the implementation of the training? Again, this text is not necessary. If you'd like to include it because it kind of helps you work throughout the problem, that's perfectly fine. But again, not necessary. Just the statistical notation here. Okay. Step number 3, we're selecting our sampling distribution for a one sample test for means. I know it's going to be a z-test. The alpha cutoff for a 0.1 alpha level for a one-tailed test. And again, it's a one-tailed test. I'll sneak down here again for our final decision here to just show you that we're only interested in this one-tailed because it's a decrease, right? We're not interested if it's different or if it increased, only decrease, so the negative end of our distribution. And because of that, we are only interested in our lower tail here. So we go to our chart and just make sure we're matching up here. So our alpha cutoff for 0.1 of a one-tailed test is negative 1.29. Moving on to computing our test statistic in step number 4. I'm going to scroll up here to our question here to just make sure we are pulling all of the correct data. Based on the problem, we know a couple of things. Our sample statistic here is 14.6, which was the average number of incidents per month from our sample here. Our population parameter here for means was 15.8 from the United States in terms of our overall average. The population standard deviation was 6.2, so you see that with our sigma sign here at the bottom. And then our n equals 30, our sample size here. Again, we're in violation of this, so that, again, should be a warning sign to you. But again, we're just going to proceed for the purposes of working through the 5-step model here. So that is the information we need to know in order to fill in our base formula here for a one sample test for means. And here's me in step 4 working through the math here on each of these steps. And you should receive approximately a z-obtained value of negative 1.06. But again, we're not done here. That's just with step 4. We now need to make a decision and interpret the results within the context of the problem. So again, I like to chart it out here. Our rejection zone is set up from our step 3. So our rejection zone is our shaded region. Again, only concerned with the lower tail here. Our critical region is negative 1.29. Our z-obtained value is now in our safety zone, our white zone here of fail to reject. So with that in mind, let's take a look at an example of how we might interpret this. Given that our z-obtained of negative 1.06 does not fall beyond our critical region of negative 1.29, we fail to reject the null hypothesis and conclude that the average number of use of force incidents did not significantly decrease following the implementation of the de-escalation training program compared to the national average. And so essentially, in this case, we found that we do not have enough evidence to significantly say that this training program worked, right? And so that would be the answer that we would give the researcher and whoever might be interested in knowing that, if it was a specific police department or whoever might be funding this particular research study, right? That would be the conclusion we would come to at that time. All right, let's head over to question number 3, our last one for this problem set. According to national data, the average number of civilian complaints against officers in mid-sized police departments is 22 complaints per quarter, with a population standard deviation of 9.5. A researcher wants to know whether the average number of complaints significantly decreased after the implementation of a department-wide body-worn camera policy. She randomly samples 75 mid-sized departments that adopted the policy and finds that the average number of complaints per quarter is 19.1. Is there enough evidence to conclude that complaints significantly decreased following implementation of the new policy at an alpha level of 0.01? You must complete the 5-step model of hypothesis testing and show your work to receive full credit, and please round your z-obtained value to the 100th place. So again, our very first step here is to determine what type of test we will be conducting. Our very first sentence here again gives away what kind of test we'll be conducting. Right off the bat, again, I see that we will be using national data. So I have a very large population, and I will be comparing that probably to a group here, again, mid-sized police departments. So I know that I have my population here. And in the very next section, I see the average number of civilian complaints. So average meaning means. So I know right off the bat, I am conducting a one sample test for means. If you wanted to double check that here, you can go over to the second sentence and see that a researcher wants to know whether the average number of complaints significantly decreased after the implementation of a department-wide body-worn camera policy. And so she sampled 75 mid-sized departments that adopted the policy. And so that is her group there. So she's comparing 75 mid-sized departments to overall national data. So one group versus the entire population. So with that in mind, let's start off with step number one, which is to state your assumptions. And so again, this is our checklist. We need to make sure that each of these actually abide by our assumptions here in order to proceed with the rest of the test. So first, we are working with an independent random sample. I see here that she randomly sampled the 75 mid-sized departments, and so we're good on that. The variable we are testing for means is interval ratio. I see that we're good on that as well because it is the number of complaints. And so it's a numerical value that has even distribution across it, and it's something that we can measure numerically. And because n is greater than 50, the sampling distribution will be normal. Unlike question number 2, which only had a sample size of 30, here I see that we have 75 mid-sized departments, and so we're good on that front. And so we do expect the sampling distribution to be normal, and we can assume that. So we have check marks on all 3 of our assumptions here. So we're good to go to proceed to step number 2. Okay, step number 2 is where we state our hypotheses. Our null hypothesis, again, we're working with means here. So we are going to have our population parameter for mean, or our symbol of mu, serve here. Again, our statement of no difference is always going to be our equal sign, followed by our population parameter, in this case, our average number of complaints per quarter. So that is 22 complaints. For our alternative hypothesis, we stay consistent with our mu symbol here. Just like question number 2, we're interested in whether or not this body-worn camera policy decreased the number of complaints. So that's why I have my less than sign here to serve as our decrease in complaints. And so again, statistical notation is all that you have to worry about here. Again, if it's helpful for you to write this out, go ahead. I find it helpful sometimes to just make sure that I'm actually matching up these symbols to what my question is asking me. And so if that's helpful for you, go right ahead. Step number 3, selecting our sampling distribution. Oh, I have a little bit of a typo here. Let me fix that for means here. Selecting sampling distribution. One sampling test for means is a z-test. And if I go right back up here, I see that I have an alpha level of 0.01. And because of that, we also have a one-tailed test. As we saw in question number 1, we were only concerned with our lower tail here, sneaking over to the end here again, but it's only the lower tail, right? Because we're only concerned with the decrease here. So with that being said, in an alpha level of 0.01, our lower tail boundary point, so what's going to serve as our rejection zone cutoff to our safety zone cutoff, is going to be negative 2.33 for an alpha level of 0.01, one-tailed, negative 2.33. All right, so now that we have that set up, let's go ahead and conduct our test here and compute our test statistic. So I'm going to scroll up here just so we can gather our information from the question itself. So based on the problem, we know a couple of things. We know that there was an average number of complaints per quarter within the sample itself of 19.1. So that's where I got that information here. Again, that is for our sample rather than the overall population. Because our population parameter, or our population average, came from our very first sentence here, which was 22 complaints per quarter. Again, that is mu here, which is also within step 2 with our hypotheses. And then a population standard deviation of 9.5. And lastly, our sample N, or sample total, of 75 mid-sized police departments. So those are the 4 pieces of information that you need to pull from the problem itself in order to go ahead and plug that into our base formula here and work through the math as well. Again, it's very helpful for me if you actually show your steps here. So if for whatever reason you might have calculated the square root wrong here, I can kind of point to that and make sure that you understand how to do that moving forward. Sometimes if you jump just from this step to the total and it might be wrong, it's difficult for me to see where you went wrong. So I can't always guide you on what might have happened behind the scenes. So that's why I really do require you to show your work here. So again, for the Z obtained, once we plug in all our steps and work through the math, you should receive approximately a Z obtained value of negative 2.64. But again, we can't stop there. We now have to chart out and figure out what kind of decision we are going to make now that we have our Z obtained value. So again, I always find it helpful to plot this out on our standard normal curve. We determined in step 3 that our Z critical value was negative 2.33. Again, our boundary between our safety zone for our fail to reject and our rejection zone. And let's take a look. Our critical value, again, negative 2.33, but our Z obtained is negative 2.64. Because that is less than our critical value, we did end up in our rejection zone. So what does that mean within the context of this particular problem? Let's take a look at how we could interpret this for that researcher, or how she may go back to those police departments about how successful or unsuccessful that body camera policy actually was. So, given that our Z obtained of negative 2.64 falls beyond our critical region of negative 2.33, we reject the null hypothesis and conclude that the average number of complaints significantly decreased after the implementation of department-wide body-worn camera policy compared to the national average of complaints. So in other words, the body cam policy was successful, right? It significantly decreased the number of complaints. And so that was a success, right? Where we saw in question 2 that the use of force training might not have been as successful. And so if we're comparing different types of policies, this might be an indicator to police departments that, hey, this one might be more successful. And so maybe we should invest more money into these types of programs versus the others. And so that's where statistics can be really helpful in terms of program evaluation. And so, like I said, you'll see very similar outline and shells that I have used for each of these interpretations. They should look almost very identical, minus the actual context of the problem, right? And so go ahead and use this structure as well. Just make sure you are actually interpreting it within the context of that problem. Again, for this one, decrease came from the question. They were interested in whether or not the complaints had significantly decreased. We also noted that in step 2 here with our alternative hypothesis. And so just keep that in mind as you're working throughout each of these problems, okay? I completely recognize that this is a lot of information, right? There's 5 steps that you have to do for each of these. And within each of those steps, there's many pitfalls that you can have along the way. I promise you, though, that it does become easier the more you do it. And that's why we're breaking this chapter into 3 separate weeks, right? Problem set 8 for 1 sample, problem set 9 for 2 sample, and problem set 10 for the mix of both of these. And within that, hopefully it becomes more comfortable for you the more you do it. And I hope these examples are helpful for you to kind of start off in getting more comfortable with that 5-step model along the way. Please, please, please stop by my office hours or set up an appointment with me if you are struggling with this. Because like I said, we will be covering this information over the next couple of weeks, and it will be a good chunk of the final quiz. And so if you're struggling with this, I want to make sure that you have a good basis of this moving forward. And so please reach out to me if you are struggling. And as always, I will see you in the next video.